Hello. Another pictorial representation of a control system, similar to a block diagram. We call it the signal flow graph. The one advantage of a signal flow graph compared to a block diagram is the ease to manipulate them and also the way how to draw them. It's consumed less space compared to the block diagram. A basic signal flow graph is composed of nodes and arrows, or we call them the branch. So nodes are just simple points. These are points, and these node they can be an output or input. This represents the signals. We call them nodes. These are called nodes. Node. This is also node. Then in between them, the transmission between them is an arrow. This one is called the branch. We call it branch. And branch, these are uh, transfer functions. So for example, if our input here, let's call it, let's call it x1, x1, and we have an output, let's just call it x2. And between them is a transfer function, it's a gain. We call it, we can just write it E1, 2. And this one, this is called the, we call it the transmission function. Transmission function. Every variable signal, every variable in a signal flow graph is represented or designated by a node. These nodes here. So control signal, the input signal, output, and so on. Those are signals. While the branch represents the transmission function. And branches are always unidirectional. The arrow denotes the direction of the signal flow. So this is the input going to the output. The signal is coming from here, going through this node. A very simple example to illustrate the signal flow graph is the Ohm's law. If you remember Ohm's law, the voltage is just equal to the product of the current. So E is just equal to I times R. Now this is an equation, so we can create a signal flow graph that will represent this equation. And that equation will be, so we have a node, two nodes, then we have a branch. The nodes are connected with the branches. So we can make our input node here, we can call it that current I, while our output is the voltage E. So that our transmission function will be R. So just like in block diagram, if you remember the block diagram, the similarities between the two, you have an input here, you have an output, and the transmission function or the gain or the transfer function is in this inside this block. So if we write the same thing, I, E, and R. So if we solve for E is just equal to the product of the input and the gain. So I times R. It's the same true as in signal flow graph. So here, if we solve for E, is this equal to the product of I and R, which is the Ohm's law. So this is the representation of the Ohm's law in a signal flow graph. Now, just like in black diagram, we also have some rules that we need to follow in signal flow graph. So what are those rules? So the first one, so these are the rules. The first one, they call it the addition rule. Addition rule. So what's the addition rule? So if we have more than, for example, you have 1, 2, 3, and 4, then we have here another node, and they are connected to each other with a branch going towards this node here. So all going toward that node. Let's call this one x1, x2, x3, and x4. And let's call the output here to be just equal to x. Let's just call it xi. And we name this the transfer function or the transmission functions. This one will be a1i. This one here will be a 2i. This one is a 3i and a 4i. So addition rule says that if you have this kind of signal flow graph, and if you want to solve for xi, then xi is just equal to the sum of all the actual value for the output. If you apply, it's just like a superposition. You remove or other sources x2, x3, x4, solve for the effect of x1, and that will be x1 times the gain. Then you do that again with x2, you do that again with x3, and you do that again with x4. So that the total output here, signal, will be the sum or the net of all the input. So in general, xi is just equal to the sum of all uh, gains and the product with that input xi. So let's just call this ji from j equals 1 up to, if this is up to x of n, then this is true until j equals n. So this is a general rule, addition rule. So if you have two, for example, so if you have two signals, so let's say here, and we have an input x1 and x2, and let's call this one g1 and g2. Then let's call this y. So applying addition rule, if I solve for y is just equal to x1 times g1 plus x2 times g2. It's somewhat similar with in block diagram. This is similar with the parallel blocks. You just need to add the effect for each of the inputs. So that's addition rule. Number 2, for the other way around, we call it the transmission rule. This is the opposite, transmission rule. So it's the opposite. You start with a common input, then you will branch out for different outputs and so on. So you can call them x1, x2, x3, dot, 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 until xn. So these are nodes. And this will be our input here. You can call it xk. Then we have uh, transfer functions or transmission functions here. A1k, A2k, A3k, and so on. A and k. So for a transmission rule, it says that if you solve for the individual output here, x1 is just equal to, it's the same, it's xk times a1k, x2 is just equal to xk times a2k, and so on. So in general, if you solve that, for example, xi is just equal to xk, you multiply it with the transmission function a ik. So you can do that here. the signal is being transmitted into different branches. That's the transmission rule. Next, we also have, or an example for this one. So if I have, for example, let's say I have two branches coming from a node. I can call this one Z, my input Z. Then I can call this X and Y. Then if this one is equal to 2 and this one is equal to -4, I want to determine what is X and Y. So using the transmission rule, X here is just equal to 2 times Z. Why? Because it's the transmission function along this branch going through the X, and the input to the transmission function is just equal to Z. So you just multiply them. So if I solve for Y will be equal to -4 times Z. So that's how we transmit signal in a signal flow graph. Another one is the multiplication rule. This is the same as the cascaded version of block diagram. Multiplication rule. So if the signals or the arrows are in cascaded or in series, so for example, this one branch is, we have another one here, then another one here, and this is cascaded or in series multiplication. So how do we deal with this type of signal flow graph? So again, if this is our input xi, then, or let's just start with x1, x1, x2, x3. Then if we have more than 3, then let's just call this xn. If there are more than another more branches connected to this, then we can call this A21, A31, and dot 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 until a n minus 1, n minus 1. So if I want to solve for xn, the output, the last output here, by using multiplication rule, xn is just equal to the product of all the gains. A21 times A31 times A41 dot 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 until an times n minus 1. Then these are all now the equivalent of this. If you want to simplify it into one branch, this will be x1, this will be xn, and this will be a21, a31 dot 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 until an times n minus 1. So you just need to multiply this with x when. Why is it true? Because if you try to solve again, what will be x2 here? X2 will be equal to a21 times the input x1. So that's x2. And that will be our input here. So if I solve x3, x3 will be equal to x2, which is a21 x1. And I just need to multiply that with a31. Then you do that again until you have this one. So this is the general multiplication rule. So example, so if we have, let's say, example, this is x and this is y, and if this is z and this is w, then I have here, let's say this is 5, 2, and 3. what is y? If I want to solve for y, so these are cascaded signal flow graphs. So if I solve for y using directly the formula here, the multiplication rule. So I just need to multiply all the gains along that path. 5 times 2. So this will be 5 times 2 times 3. And you multiply it with the input x. So that y will be equal to 5 times 2, 10 times 3, 30 times x. So the equivalent of this in a single branch signal flow graph, we have an input x, output y, and this one is just equal to 30. So if I solve for y, y is just equal to 30 times x. So that's how we simplify signal flow graph. Those are some rules that we need to consider when we are treating signal flow graphs. And before we end this, there are also some definitions that we need to define and you need to understand. You need to identify in a certain signal flow graph, because later on, when we try to solve the complete transfer function of a signal flow graph, or the overall gain or the overall transfer function, then we will be identifying these different definitions. So what are those definitions? So we start with definitions. The first one is a a path. So PATH, path. A path is a continuous unidirectional successions of branches along which there's no node being passed more than once. So succession, no node being passed more than one, more than once, more than once. So in this example, in this signal flow graph, so what will be the path here? We have multiple paths here. For example, x1 to x2 to x3 to x4. So that's a path. That's considered to be a path. And we can also have another one is x1, x2. Then you flow here, you move here through x4. That's another path. We can also consider this one as a path from x2 to x3, then you go back to x2. So that's still a path. We can also consider also x1 to x2 uh, and directly moving here to x4. So those are paths. So we can draw that example of paths. The first one is that direct path, that is on x1, x2, x3, and x4. Later on, we will define these different paths. They are different. We call them in different ways. Another one, we can also consider a path here. It's a special path. This one, this is x2 and this is x3. That is also considered the path. The other one is, if you have that way, and this is x1, this is x2, and this is x4. This is also considered the path. So no more than once. Then we also have input nodes. Another definition, we call them input nodes, or they are also called the source node. They are called source because they are sources. It's a node, input node, and these nodes are nodes that has signals going outward, outgoing branches. So for example, for x1, what's the branch that is connected to this node? We have this branch here, A21. and the direction is going outward. So we can call this one an input node or a source node. Another example here, I think that's the only input node here. We only have x1. So the example for an input node is this x1, node x1. So that's an input node. Another one is the output node. So for output node, they are sync. They are called sync. Source, then we have sync. So it's the other way around. For input node, again, these are branches going out connected to the node, going out. While for an output node or a sync, branches going inward, incoming, going in to the node. So in our example here, we have export as our output node because there are incoming entering this nodes. We have this one and this branch. So we consider export as an output node. So export is an output node. If the node contains both incoming and outgoing, so for example, x2 here and x3, there are branches that are connected to x2 that are incoming, a21 and a23, and there are also branches that are outgoing. They call them the mixed node. They are not input nodes, they are not output nodes. We call them mixed nodes. So both incoming and outgoing branches. Next, so those are nodes, and we already know the lines that connects nodes. We call them the branches. We can define them again. Branches. These are the line segment uh, connects nodes together. So they call it branches. And the value for that branches, we call them these A to 1, we call them the transmission functions, or some books, transmission function, or they also call it transmittance. Transmittance. These are the value of the branches. So those are nodes and branches. We also have paths. So under path, we have different types of path. The first one, the first type, we call it the forward path. Forward path. What is a forward path? This is a path. This is a path from the from input to the output node. To the output node. It's a path that connects the input to the output node. So in our example here, we have two paths. We have two paths that connects the input. Our input is x1, our output is x4. The first path is this one from x1, x2, x3, and x4. So that is the forward path. Another one is you start with the input again, you go to x2, but instead of going to x3, you can use a42 to go to x4. So that's still considered a forward path. So these two, this one and this one, are considered forward path. Forward path. We can have more than one, we can have more than two. It depends on, as long as the input and the output are connected. But be careful. Uh, you need to follow the direction of the arrows. It's a path, so you need to follow the arrows. You cannot go the other way around. So for example, x1, x2, then you go here, E23. That is not considered the path because it's in the different direction. So these branches, remember the definition of branches, they are unidirectional. Unidirectional means they are only one direction. They're not bidirectional. So if the arrow points to that direction and that is the only direction the signal will flow, it's a forward path. Next, we have also what we call the feedback path. Feedback. Feedback path, or they also call it or feedback loop. Feedback loop. So what's a feedback path or feedback loop? This is a path that originates, originates and terminates, terminates with the same node. So here in our example, a a loop or a feedback path is an example of a feedback path is this one from x2 to x3 and it goes back again to x2. So this is a feedback or a loop. We cannot consider a feedback path a x2 going here to x4 and go back to x2 because the direction of the arrows is unidirectional. It only goes to that direction. So this is not considered here. This is not considered a loop, not a loop or a feedback path. We can only consider this one as a loop. This is a loop, a feedback loop or feedback path. Feedback path. How about this one here? It also starts with the same node and ends with the same node. But the only difference with the other loops, this is a type of a loop. It's also a loop because it starts with the same node and ends or terminates with the same node. But the only difference is it only has uh one direction, one branch connecting to that one. And that's called that is we call it, it's a special loop. We call it self loop. Self loop. It only consists of a single branch. A loop that consists of one branch. It's a loop that consists of one branch. Okay, then the transmittance or the transmission functions, we can also call them the gains. So in short, we can just call it gain. It's easier to write than these two. So the gains A21, A32, and those are gains. And there are different types of gains. The first one is the path gain. Path gain. When we say path gain, this is a gain in a loop or in a path, in a certain path. It depends on it's a forward path or a feedback loop or feedback path. So it's a path gain. So if we have, for example, here, let's say this forward path here, what will be the forward path gain? The gain will be equal to, if this is A21, this one is A32, and this one is A33. So the forward path gain will be equal to A21 times A32 times A33. Why do we need to multiply them, board? Because they are cascaded. That is the meaning of the path gain. That's the total gain of this path. So here, the loop gain, if this is a loop, if this is A32, this is A23. So if we want to solve the loop gain, that is just equal to A32 times A23. And for this one, if this is A21 and this is A41, then the forward path gain will be A21 times A41. That is the meaning of a path gain. It's the gain along the path. It's the product of the gains. Product of the gains or transmission functions. Transmission functions along the path. So it can be a forward path gain, and if it's a loop, we call it a loop gain. So it's the same thing, but it's just a loop. So these are different definitions. We also have other definitions that we need to define. So loop, this is the product of gains along a loop. We also have what we call the non-touching loops. Non-touching loops. So when we say non-touching loops, so if you have here a signal flow graph with 3 and 4. Then, so here, if we define a non-touching loops, there are actually two non-touching loops in this one. So what are those non-touching loops? We have this loop here and this another loop here. They are two non-touching loops. So if there are other loops that is involved here, and you can include them. But when we say non-touching loop, it means they don't have no common nodes. No common nodes. So these two here this cannot be considered non-touching loops because they have a common node here. They're connected at this node. So we can only consider this one and this one as non-touching loops. Okay, so those are non-touching loops. We will be needing that later on when we go to the Mason's gain formula when we try to solve for the total transfer function of a signal flow graph. So these are the different definitions and fundamentals of a signal flow graph.